Hello and welcome to my astronomy course. I'm Professor Nickolay Zosimovych from School of Robotics, Xi'an Jiatong Liverpool University in China. And I'm excited to lead you on this journey over the next spring and summer semester. The first I want to say about the language. First of all, from my Ukrainian and another students, for which the English is not the name. Don't worry about your English. We're all here, except knowing something interesting about astronomy. We're here to practice in it. So simply listen, look, and try to understand my information. Okay? And certainly relax. Oh, another, your mates attended here have got the same language. Okay? So, and why I am preferring namely this language? Because I hope your dream became astronaut or working with aerospace technology in your nearest future. All right? And for this reason, English is the most suitable language. English is a language for scientific communication. It widely used um, in industry, aeronautics, scientific, navy, press, and certainly in aerospace science. And so this is a nice reason to use this language and master it during our astronomy. So, let's start. Remember about question. Immediately, if you need to clarify something, use our chat. Okay? So, do not forget our motto in Latin language, per aspera ad astra. As you study astronomy, you will learn about yourself. You are a planet walker. And this lecture will give you a preview of what it means to live on a planet that whirls around a star and drifts through a universe of other stars and galaxies. You owe it to yourself to know where you are. That is the first step to knowing what you are. In this lecture, you will meet three essential questions about astronomy. Where are you in the universe? And how does human history fit on the time scale in the universe? And why should you study astronomy? As you study astronomy, you will see how science gives you a way to know how nature works. And namely in this lecture, you can begin by thinking about science in a general way. Later, a bit later, our lectures will give you more specific insights into how scientists work and think and know about nature. And this class is just a jumping off place. From here onward, you will be exploring deep space and deep time. And next lecture begins your journey to looking at the night sky as seen from Earth. Well, first, let me tell you a brief about our study plan. We will be meeting once or sometimes twice a week. Our classes will be start at evening time, I hope this time is useful. Okay, so let's start. A bit later, during summer session, we will be meeting at this building. Hope you all recognize our all well-known Zhytomyr Sergei Korolev National Space Museum. And this is our headquarters. Now, let's view to the future. As you study astronomy, you will learn about yourself. As I just mentioned, you are a planet worker. And this model will give you a preview of what it means to live on a planet that whirls around a star, that drifts through a universe to other stars and galaxies. You owe it to yourself to know where you are. And that is the first step to knowing what you are. As you study astronomy, you will see how science gives you a way to know how nature works. In this module, you can begin by thinking about science in a general way. Later modules will give you more specific insight into how scientists work and think and know about nature. And this module is just a jumping off plane. Remember, please. From here onward, you will be exploring deep space and deep dive. As you study astronomy, you are learning about yourself. And knowing where you are in space and time is a critical part of the story of astronomy. To find yourself among the stars, you can take a cosmic zoom right out through the universe to preview the kinds of objects you are about to study. You can begin with something familiar. And this, in this figure, shows a Zhytomyr region about 50 feet across, occupied by a human being, a sidewalk, and few trees, all objects whose size you can understand. A successive picture in this cosmic zone will show you a region of the universe that is 100 times wider than the preceding picture. That is, each step will widen your field of view, the reason you can see in the image by a factor of 100. Widening your field of view by a factor of 100 allows you to see an area 1 mile in diameter. Look at this figure, please. People, trees, and sidewalks have become too small to see. But now you see a city center, former Izmerital company, and surrounding streets and houses. The dimensions of houses and streets are familiar, and this is still the world you know. Before leaving this familiar territory, you should make a change in the units you use to measure size. Astronomers, as do all scientists, use the metric system of units because it is well understood, worthwhile, and more importantly, because it simplifies calculations. And this figure is an infrared photograph, which is why healthy green leaves and crops shows up as a red. Human eyes are sensitive to only a narrow range of colors. As you explore the universe, you will learn to use a wide range of other colors, from X-rays to radio waves, to reveal sights invisible to unaided human eye. You will learn much more about infrared, X-rays, and radio energy in a later module. At next step in your journey, you can see your entire planet, which is nearly 13,000 kilometers in diameter. The photo shows most of the daylight side of the planet. It also rotates on its axis once a day. exposing half of its surface to daylight at any particular time. It is the rotation of the planet that causes the cycle of day and night. The rotation of Earth carries you eastward, and as you cross into the darkness, you see the sunset in the west. The blurriness you see at the extreme right of the photo is the boundary between day and night, the sunset light. This is a good example of how a photo can give you visual clues to understanding a concept. Special questions called learning to look at the end of each module give you a chance to use your own imagination to connect images with the theories that describe astronomical objects. Enlarge your field of view by a factor of 100, and you see a region 1,006,100 kilometers wide. Earth is a small blue dot in the center, and the moon, whose diameter is only 1/4 that of Earth, is an even smaller dot along its orbit 380,000 kilometers away. These numbers are so large that it is inconvenient to write them out. Astronomy is sometimes known as the science of big numbers, and soon you will use numbers much larger than these to discuss the universe. Rather than writing out these numbers as in the previous model, it is convenient to write them in scientific notation. This is nothing more than a simple way to write very big or very small numbers without using lots of zeros. In scientific notation, 380,000 becomes 3.8 times 10 in power 5. The universe is too big to discuss without using scientific notation. Okay? When you once again enlarge your field of view by a factor of 100, Earth, the moon, and the moon's orbit all lie in the small red box at lower left on the TV. Now you can see the sun and two other planets that are part of our solar system. Our solar system consists of the sun, its family of planets, and some smaller bodies such as moons and comets. Like Earth, Venus, and Mercury, our planet's small, spherical, non-luminous bodies that orbit a star and shine by reflected light. Venus is about the size of Earth, and Mercury is just over a third of Earth's diameter. On its diagram, they are both too small to be seen as anything but tiny dots. The sun is a star, a self-luminous ball of hot gas that generates its own energy. Even though the sun is 109 times larger in diameter than Earth, it too is nothing more than a dot in this diagram. And this diagram represents the area with a diameter of 1.6 times 10 in power 8, all measured in kilometers. One way astronomers simplify calculations using large numbers is to define larger unit of measurement. The average distance from Earth to Sun is the unit of distance called the astronomical unit AU. A distance of 1.5 times 10 in power 8 kilometers is this distance. One astronomical unit. Now you can see that the average distance from Venus to the Sun is about 0.72 astronomical units. And the average distance from Mercury to the Sun is about 0.34 astronomical units AU. These distances are averaged because the orbits of the planet are not perfect cycles. This is particularly apparent in the case of Mercury. Its orbit carries it as close as the Sun as 0.307 astronomical units, and as far away as 0.467 astronomical units. You can see the variation in the distance from Mercury to the Sun in this figure. Earth's orbit is more circular, and its distance from the Sun varies by only a few percent. Enlarge your field of view again, and you can see the entire solar system. The details of the preceding picture are now lost in the red square at the center of this diagram. You see only the brighter, more widely separated objects. The Sun, Mercury, Venus, and Earth lie so close together that you cannot see them separately at this scale. Mars, the next planet outward, lies only 1.5 astronomical units from the Sun. In contrast, Jupiter, Saturn, Uranus, and Neptune are farther away and so are easier to place in this diagram. They are called dwarfs, far from the Sun's world. Light from the Sun reaches Earth is only 8 minutes, but it takes over 4 hours to reach Neptune. When you again enlarge your field of view by factor of 100, the solar system vanishes. The Sun is only a point of light, and all the planets and their orbits are now crowded into the small red square at the center. The planets are too small and too faint to be visible so near the brilliance of the Sun. Nor are any stars visible except for the Sun. The Sun is a fairly typical star, and it seems to be located in a fairly average neighborhood in the universe. Also, there are many billions of stars like the Sun. None are close enough to be visible in this diagram, which shows a region only of 11,000 astronomical units in diameter. The stars are typically separated by distance about 10 times larger than the distance represented by the diameter of this diagram. In next figure, your field of view has expanded to a diameter of a bit over 1 million astronomical units. The Sun is at the center, and at this scale you can see a few of the nearest stars. These stars are so distant that it is not reasonable to give their distances in astronomical units. To express distances so large, astronomers define a new unit of distance, the light year. 1 light year is the distance that light travels in 1 year, roughly 1,013 kilometers or 63,000 astronomical units. Sorry, I just given you some mistake and only realized what is 1 light year. It's 10 in power 13 kilometers, okay, for 63,000 astronomical units. And it is a common misconception that a light year is a unit of time. And you can sometimes hear the term misused in science fiction movies and TV shows. The next time you hear someone say, "It will take me the light years to finish my history paper," you can tell that person that a light year is a distance, not a time. Okay? The diameter of your field of view in this figure is 17 light years. Another common misconception is that stars look like disks when seen through a telescope. Also, stars are roughly the same size as the sun. They are so far away that astronomers cannot see them as anything but points of light. Even the closest star to the sun, Alpha Centauri, only 4.2 light years from the Earth, and looks like a point of light through even the biggest telescope on Earth. Furthermore, any planets that might circle other stars are much too small, too faint, and too close to the glare of their star to be visible directly. Astronomers have used indirect methods to detect over 200 planets orbiting other stars, but you can't see them by just looking through a telescope. In this figure, the sizes of the dots represent not the sizes of the stars, but their brightnesses. This is a custom in astronomical diagrams, and it is also how star images are recorded on photographs. Bright stars make larger spots on a photograph than faint stars, so the size of a star image in a photograph tells you not how big the star, but only how bright the star looks. Okay? And in this figure, you expand your field of view by another factor of 100, and the sun and its neighboring stars vanish into the background of thousands of other stars. The field of view is now 1700 light years in diameter. Of course, no one has ever joined thousands of light years from Earth to look back and photograph the solar neighborhood. So this is a representative photograph of the star. The sun is a relatively faint star that would not be easily located in a photo at this scale. If you again expand your field of view by a factor of 100, you see our galaxy, a disk of stars about 80,000 light years in diameter. A galaxy is a great cloud of stars, gas, and dust held together by combined gravity of all the matter. Galaxies range from 1,500 to over 3,100 light years in diameter and can contain over 100 billion stars. In the night sky, you see our galaxy as a great cloudy wheel of stars ringing the sky. This band of stars is known as the Milky Way, and our galaxy is called the Milky Way galaxy. How does anyone know what our galaxy looks like if no one can leave it and look back? Astronomers use evidence and theory as guides and can imagine what the Milky Way looks like. And then artists can use those scientific conceptions to create a painting. Many images in our lectures are artists' rendering of objects and events that are too big or too dim to see clearly, emit energy your eyes cannot detect, or happen too slowly or too rapidly for humans to sense. These images are not just guessing. They are guided by the best information astronomers can gain. As you explore, notice how astronomers use their scientific imagination to understand cosmic events. The artist's conception of the Milky Way, reproduced in this figure, shows that our galaxy, like many others, have graceful spiral arms binding outward through its disk. In a later module, you will learn that stars are born in a great cloud of gas and dust when they pass through the spiral arc. Our own sun was born in one of these spiral arcs. And if you could see it in this picture, it would be in the disk of the galaxy about 2/3 of the way out from the center. Ours is a very large galaxy. Only a century ago, astronomers thought it was the entire universe, an island cloud of stars in an otherwise empty vastness. Now they know that our galaxy is not unique. It is only one of many billions of galaxies scattered throughout the universe. When you expand your field of view by another factor of 100, our galaxy appears as tiny luminous speck surrounded by other specks. And this diagram includes a region of 17 million light years in diameter. And each of the dots represents a galaxy. Notice that our galaxy is a part of a cluster of a few dozen galaxies. Galaxies are commonly grouped together in such clusters. Some galaxies have beautiful spiral patterns, like our own galaxies, but others do not. Some are strangely distorted. One of the mysteries of modern astronomy is what produces these differences among the galaxies. Now is a chance for you to correct another common misconception. People often say galaxy when they mean solar systems, and they sometimes confuse those terms with universe. Your cosmic zoo has shown you that it's different. The solar system is the sun and its planets. Our galaxy contains our solar system plus billions of other stars and whatever planets orbit around them. The universe includes everything, all the galaxies, stars, and planets, including our own galaxy and our solar system. If you again expand your field of view, you can see that galaxies tend to occur in clusters, and that the clusters of galaxies are connected in a vast network, as you see in this picture. Clusters are grouped into superclusters, clusters of clusters, and the superclusters are linked to form long filaments and balls outlining nearly empty voids. These filaments and balls appear to be the largest structures in the universe. Were you to expand your field of view another time, you would probably see a uniform fog of filaments and balls. When you puzzle over the origin of the structure, you are at the frontier of human knowledge. Next lecture will be when is now. And do you satisfied from today's class? Do you have any questions or propositions? You might leave it in the comments in our video. Do not hesitate to stop me immediately after you're seeing this class. And every moment if you want to clarify something to you. Okay? I hope you enjoyed this lecture, and I'm looking forward to see you next time. Bye.